Okay, in the last lecture we studied how to determine the microstates or how to construct the microstate table, and we have taken the example for D2 configuration. Now we will see the construction of microstate table or determination of term wave functions for NP3 configuration. So there are 3 electrons in the p orbital, and there are 3 ml values under the p orbital. That is, ml values are +1, 0 and -1. First we will determine the total number of microstates for this NP3 configuration. So again, using the n factorial equation, so the capital N, that is total capacity of p orbital, is 6, small n, that is actual number of electrons present, is 3, and therefore n minus n is equal to 6 minus 3, that is 3. Therefore, total number of microstates for P3 configuration are, according to n factorial equation, 6 factorial by 3 factorial small n factorial into n minus n factorial, that is 3 factorial. So this will come to 6 into 5 into 4 into 3 factorial by 3 into 2 into 1 into 3 factorial. So 3 factorial will get cancelled. 2, 6 by 2, 3, and therefore the answer comes to be 5 into 3, 15, 15 into 4, 60 by 3. Therefore, total number of microstates for P3 configuration is 20. So now we have to determine the term wave functions, means we have to represent the P3 configuration, that is 3 electrons with respect to their spin values and orbital quantum number values. For determination of microstate table, we should know the ml values, and ml values are obtained by summation of the individual orbital quantum number, and as there are 3 electrons, the 3 ml values, that is ml for first electron, ml for second electron and ml for third electron. As the highest possible ml for each electron is +3, so the first electron can have the ml value of +1 as well as 0 as well as -1. Similarly, the second electron can also have theoretically ml value of +1, 0 and -1, and the third electron can also have ml values of +1, 0 and -1. So in the theoretically highest possible value ml, it will be +3 to -3, and all middle values are possible due to different combinations of ml values for 3 electrons. So the ml values for P3 configuration available are +3, +2, +1, 0, -1, -2 and -3. In the same way, we can obtain the total spin values for P3 configuration, and total spin values are obtained by summation of ms, that is individual spin values. Therefore, as there are 3 electrons, it will be equal to ms1 spin value of first electron, ms2 spin value of second electron, and ms3 spin value of third electron. As only 2 values are possible for each electron, that is +1/2 and -1/2. So the first electron can have either +1/2 or it may have -1/2 spin. Similarly, second electron can also have the +1/2 as well as -1/2, and the third electron can also have, it is possible to possess +1/2 or minus 1/2 spin. So in the possible cases, plus if all the 3 electrons can have plus 1/2 plus 1/2 plus 1/2, the total spin comes to be 3/2, and if all are having minus 1/2 spins, then the total spin comes to be minus 3/2, and all middle intermediate combinations, that is 2 may have plus 1/2, 1 may have minus 1/2, so plus half 1 and minus half, it will become plus half, therefore plus half is also possible. And in other case both electrons, 2 electrons may have minus 1/2, that is minus 1, and third electron may have plus 1/2, therefore minus 1/2 minus 1/2 minus 1 minus half, that is minus 1/2. So the possible ms values for P3 configuration comes to be 3/2, 1/2, minus 1/2 and minus 3/2. So next job is to construct the microstate table by using these ms and ml values. So let us find out the microstates in the form of table. So as in case of D2 configuration, here make the first column. Here ms values will be written down, and here write down the ml values in this column. So possible ml values were plus 3, plus 2, plus 1, 0, minus 1, minus 2 and minus 3. And the possible ms values are 3/2, 1/2, minus 1/2. ms values are 3/2, 1/2, minus 1/2 and minus 3/2. So first we have to write down the p configuration, or the orbitals in the form of blocks with ml values plus 1, 0 and minus 1. Now for this plus 3 ml and 3/2 ms, all the 3 electrons in the p configuration should have, in order to get the microstate at this place, the total ml should be plus 3 and total ms should be 3/2. So it is not possible. If we have to get total ml of plus 3, then we will have to arrange all the 3 electrons in this first orbital. So it is not possible, or this arrangement is not allowed according to the Hund's rule of maximum multiplicity or the Pauli's exclusion principle, and therefore we will not get any microstate at this place. Similarly, any microstate at this place, because first we have to keep the total ml of plus 3 and then we have to adjust the ms values. So it is not possible to get any microstate under the ml plus 3 or any ms value. Now for this plus 2 ml value, again, in order to get plus 2 ml, at least 2 electrons should be arranged in the ml plus 1, and both should have the up spins, that is plus 1/2 plus 1/2. Again this arrangement is not possible, and therefore in this place also we will not get any microstate. Now for this plus 1/2, it is possible to arrange the electrons. So 2 electrons can be arranged in plus ml value, so that the ml value of these 2 electrons becomes plus 2, and the ms for this configuration, these 2 electrons become 0, and if the third electron is arranged in ml 0, then it is possible to obtain, for this configuration, it is possible to obtain ml value of plus 2 and ms value of plus half. So plus half 1 and minus half, that is plus 1 half, and therefore this microstate can be shown as the first electron here 1, orbital quantum number 1 for first electron, for second electron orbital quantum number 1, and for third electron orbital quantum number is 0, and their spins are written on the heads of these microstates orbital quantum numbers, that is plus 1 second electron, minus half, and the electron in 0 ml value, it is having plus value. So as we are getting here the plus 1 half and plus 2, we can get here minus 1 half total spin and ml, plus 2 can be constant if just we change the spin of this value to minus half. So it becomes a new microstate for which 2 minus half and 1 plus half, therefore the total will become minus 1 half, and hence the microstate here we get is again 1, 1, 0 plus minus, these are same as here, but the electron spin of 0 ml it changes to minus. As we are not getting any microstate at this place, we will also not get any microstate here. It means both the electrons cannot be arranged with down spin to get the minus 3/2 value. Then next for plus 1 ml, see the microstates. Again, in order to get the plus 1 and plus 3, but total spin 3/2, all the 3 electrons should be having plus 1 half, and in order to have all the 3 electrons plus 1 half, we have only to arrange electrons like this according to Pauli's exclusion principle and Hund's rule of multiplicity. But here if we arrange such electronic configuration, then the total ml changes, it becomes 0, plus 1, minus 1 and 0, total becomes 0. So this arrangement is not possible for the first place. So here also we will not get any microstate. Now for this plus 1 half spin and plus 1, we can arrange the electrons, the 2 electrons, 1 electron in plus 1 and 2 electrons in the 0 ml value. So for this again 2 electrons are up spin, 1 electron down spin, spin gets cancelled and the total spin remains plus 1 half. So under plus 1 half, and total ml, that is for both these electrons total ml value is 0, and for this electron it is 1. Therefore this microstate can be written as 1, 0, 0, 1, 0, 0, and their spin values are, for 1 it is plus 1 half, and for 2 electrons in 0 the plus and minus. From this microstate we can get the microstate for minus 1 half spin just by changing the spin of this electron. So here 1, the state 0, 0, and we have to change the spin minus, these spins will not change. So the now total 2 minus 1 plus, and therefore minus 1 half spin. As we are not getting here any microstate, we will not get here any microstate. One more possibility for getting this total ml 1 is as the electrons 1, 0 and 1, 1, 2 electrons in plus 1 and 1 electron in minus 1. So it is possible. So one more microstate we get at this position, and that microstate can be shown as 1, 1 and minus 1. In this orbital 2 electrons, 1 plus 1 half, second minus 1 half, and in minus 1 ml the spin is plus 1 half. from this microstate we can also get here the another microstate just by changing the spin of the electron in minus 1 ml. So the microstate will be 1, 1, minus 1. Here plus minus will remain same and now it will become minus. So here we cannot change these two electrons. The two electrons in the same orbital are equivalent and therefore whether the first electron plus or second electron plus, it doesn't matter. So in this way the total 4 microstates for the ml value of plus 1. Now for the 0, in order to get 0, now it is possible for the 0 ml and total ms of 3 by 2, we can arrange all the 3 electrons each having plus 1/2 in the 3 different ml values. Now this arrangement is possible, which gives total ml plus minus 0, 0, total ml 0, and all the electrons are up spins. Therefore total ms plus 1/2 plus 1/2 plus 1/2, that is 3 by 2. So this microstate can be shown as 1, 0, minus 1. So these are orbital quantum numbers of corresponding or respective electrons, and the spins are plus, plus, plus. In the same way, we can write down all these 3 electrons down spin, which is possible first, second and third, and for this arrangement we get the microstate under minus 3 by 2 spin. Therefore we can write the same orbital quantum numbers 1, 0, 1, but the spins are, all spins are minus 1/2. So total minus 3 by 2. Now from this microstate, it is possible from the first microstate we can make total 3 microstates by changing spins. So in the first microstate, second microstate and third microstate, we can arrange, we can adjust the spins such that here 1, 0, minus 1, 1, 0, minus 1, 1, 0 and minus 1. We can, in order to get plus 1/2, we can show the spins of any 2 electrons plus 1/2 and 1 electron minus 1/2. So in this arrangement, first electron is plus 1/2, second electron plus 1/2, but third electron is minus 1/2. So total spin 2 plus 1 minus comes plus 1/2. In the second arrangement, we can change the spin of this middle electron, that is 0, minus 1/2 and the minus 1 we can make plus 1/2. So now the arrangement plus, minus and plus. Similarly, now we can change the spin of first electron down spin and these 2 electrons are up spin. So this is a new microstate. First electron minus 1/2, second electron plus and third electron plus. Now from the same microstate under minus 1/2 total spin, we can obtain 3 microstates. Now here we have kept 2 electrons up spin, 1 electron down spin. Now for this minus 1/2 spin, we can keep 2 electrons down spin, that is to spin value minus 1/2 and 1 electron up spin. So the possible arrangements are again the same orbital values 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. And the values first electron plus, next to minus, then first electron minus, third electron minus, and this one plus, and first 2 minus and third one is plus. So in any combination you can see that there are 2 electrons with minus 1/2, 1 electron with plus 1 half, so total spin comes to be minus 1 half. So in this way, total microstates 1, 2, 3, 4, 5, 6. In the same way, we will get these 6 microstates. Uh, 1, 2, 3, 4, 5, 6, 6 plus 6, 12, and middle are 8 microstates. So here plus 3 plus 2 plus 1. In the same way, we will not get at minus 1, minus 2 and minus 3. At the plus 2, here we will get under the plus 2, 1 half, like the under plus 1 half, and minus 2, we will get the same microstate for plus 2, and minus 2, we are getting the microstate minus 1, and 0, and the same spins, that is plus, minus and plus. In the same way, here we will get the microstate minus 1, 0, and the spins are plus, minus, minus. Here we will not get any microstate, and for the plus 1 ml value, from these microstates we will get 1, 0, minus 1, 0, 0. In order to get minus ml value, we have to just change the sign of orbital quantum number for the plus 7 values. So minus 1 here 1, 0, 0. So minus 1, 0, 0, and same spins plus, plus, minus, because total spin is not changing, only total ml is becoming negative. In the same way, the second microstate, here we will get, that is minus 1, and plus 1. Minus 1, and plus 1. And the spins will be same, that is plus, minus, plus. In the same way, here minus 1, 0, 0, minus, plus, minus, and next microstate minus 1, and plus 1, and spin values plus, minus, minus. So in this way, the microstate table is complete for the NP3 configuration. So total number of microstates by n factorial equation we have obtained is 20. So we can count here for 20, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 and 20. So in this way, 20 microstates can be determined by using total MS and total ML values. Now we have to assign these microstates to the corresponding arrays terms. So we begin with this first microstate, which has highest ML and the highest MS value. So as the ML value is plus 2, the term symbol for the term from which this microstate belongs is the D, because the term symbol depends upon ML value or orbital quantum number. Now the total spin for this microstate is 1/2, or we can say plus minus gets cancelled, so plus 1/2. So when the total spin is 1/2, either plus 1/2 or minus 1/2, the 2s plus 1, that is the multiplicity, comes to be 2 into plus half plus 1. So 2 get cancelled, 1 plus 1 is equal to 2. So its multiplicity of this term is 2, and this term is called as doublet D. Now doublet spin multiplicity 2 means the 2 spin values are possible, and these 2 spin values are, this is plus 1/2 and minus 1/2. And for D, the orbital multiplicity for D term is 5, and this D term orbital multiplicity, that is orbital quantum numbers, the doublet D term will be obtained or will occur in the ML values from plus 2 to minus 2, that is 5 ML values and 2 ms values. So total this will be WT, this term will also belong to WT. First term goes to WT, only for 2 total spin values, WT minus 2 WT and WT. So in this way 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. 10 microstates belong to WT arrays term out of 20 microstates. Then next microstate for the nomenclature or assignment to the term, it comes to be this microstate. These are assigned to WT. So next microstate to be assigned is this one. For this microstate, the total ml value is plus 1, that is 1, and therefore the term symbol is P. Term symbol is capital P, and for this term again the total spin is plus 1/2, and so when the spin is plus 1/2, the multiplicity comes to be 2, therefore it is WT term. WT again multiplicity, spin multiplicity 2 means this term will occur under 2 spin values, and those 2 spin values are plus 1/2 and minus 1/2, and this term also occur for 3 ml values because there are 3 orbital quantum P, that is ml values, so it will occur under plus 1, 0 and minus 1. So we assign total 6 microstates to this WT. So WT, then here second goes to WT, here second goes to WT, here this second goes to WT, and it goes to WT. Now the term which remains to be named, microstate which remains to be named, that is this microstate, and for this microstate the ml value is 0, so term symbol is S, and the ms value is 3/2. For this term ms value is 3/2, so here for 3/2, when total spin is 3/2, 2 into 3/2 plus 1 is equal to 2 gets cancelled, 3 plus 1, 4. So the term is quartet. Quartet means this term will occur in 4 spin values, and these 4 spin values are 3/2, 1/2, minus 1/2 and minus 3/2. So this is the first quartet S, and for S the orbital quantum number 0, therefore only 1 ml value is there, and that ml value is 0, therefore this quartet S will occur under all these spin values but at the only single ml value, that is 0. So quartet S, then quartet S, and this is quartet S. So in this way we have assigned on the microstates to different arrays terms. Then next we will see the total degeneracy of the P3 configuration, and for this total degeneracy we have to follow the equation, that is twice N plus 1 into twice S plus 1. So the total degeneracy can be calculated for the P3 configuration, or for individual. First we will obtain the total degeneracy for the arrays terms for P3 configuration, for P3 and P3 or 2P3 configuration. So the terms obtained are, first is WT. For WT, the equation for total degeneracy is twice N plus 1 into twice S plus 1. For D term, N is equal to 2, and here this 2 is the spin multiplicity, means 2S plus 1. Plus 1 is 2. So total degeneracy 2 into value of L, 2 plus 1 into 2 is equal to 5 into 2, that is 10. So for doublet D, total degeneracy is equal to P. The next term we obtain is doublet P. For doublet P, L value is equal to 1 and S value is again 1/2. So this doublet P is equal to twice S plus 1. So we can calculate total degeneracy as 2 into L value 1 plus 1 into spin multiplicity 2, that is 2 into 1, 2 plus 1, that is 3 into 2. So total degeneracy for doublet P term comes to be 6. And next term is quartet S. For quartet S, L is equal to 0 and total spin, that is S is 3/2. So when S is 3/2, spin multiplicity is 4. So it's equal to 2 into 0 plus 1 and spin multiplicity 4. So 1 into 4, that is total degeneracy of the quartet S is 4. So 4, 6, 10 plus 10. So total degeneracy is equal to total number of microstates. So total degeneracy, now we can say that total degeneracy of P3 configuration is equal to total degeneracy of NP3 configuration is equal to 20. Let us determine the spin orbit coupling values which are obtained by the equation. So J values first for doublet D term, and these are obtained by using the equation L plus S to L minus S. For D, L is equal to 2 and S is equal to 1/2. So the total J values comes to be L plus S, that is 2 plus 1/2, to L minus S, that is 2 minus 1/2. So it will be equal to 5/2 to 3/2. That is only 2 J values, 5/2 and 3/2. So the doublet D will be splitted into 2 energy levels with doublet D term will be splitted into 2 energy levels, that is doublet D and doublet D, and afterwards we will determine which is the ground and which is the highest energy level. Next, second one is doublet P. For doublet P, L is equal to 1 and S is equal to 1/2. So J values for doublet P will be equal to again L plus S to L minus S is equal to L1 plus S 1/2 to L1 minus 1/2 will be equal to 1 plus half 3/2 to 1 minus half, that is 1/2. Again 3/2 and 1/2, that is doublet P term will be splitted into 2 J values or 2 energy levels with 2 J values, that is doublet P will be splitted into 2 terms, doublet P and doublet P with 3/2 and here 5/2 and 3/2, here 3/2 and 1/2. Later on we will decide which is ground state. Similarly quartet S. Quartet S, for quartet S, for S term L is equal to 0 and S is equal to 3/2. So the J values for quartet S will be obtained by using L plus S to L minus S. So L is 0 plus S is 3/2 to L is 0, S is 3/2. So 0 plus 3/2, 0 minus 3/2 is equal to plus 3/2. 2 minus 3/2 means plus 3/2 plus 1/2 minus 1/2 and minus 3/2. So these 4 J values are obtained by spin orbit coupling for quartet S term. So quartet S is split into 4 J values plus 3 by 2 to minus 3 by 2. So now let us determine the energy level sequence for all these terms and the J values. According to Hund's rule, the term which has highest spin multiplicity is ground state at the ground state, followed by the next term having highest spin multiplicity, but these two terms have same spin multiplicity. Therefore, according to second Hund's rule, the term which has highest orbital multiplicity is at lower energy, and therefore the energy level sequence for P3 configuration, first P3 configuration is splitted into 3 terms. It is splitted into 3 terms, and these 3 terms, ground state will be quartet S, followed by doublet D, and followed by doublet P. Further, doublet P is splitted into 2 J values, doublet D is splitted into 2 J values, and quartet S is splitted into 4 J values. So now the J values, as the P3 configuration is less than half full, it is just half full. As it is half full, the lowest J value will be at ground state. So quartet S, the lowest quartet S will have minus 3 by 2 J value, and followed by minus 1/2, plus 1/2, and 3 by 2, according to the Hund's second rule. For this doublet D, we have obtained 2 J values, doublet D, 5 by 2 and 3 by 2. Again, as the configuration is half full, the lowest J value, that is 3 by 2, is at lower energy, and highest J value is at higher energy. Similarly, doublet P and doublet P, for which we have obtained 2 J values, that is plus 1/2 and 3 by 2, lower J value plus 1/2 will be at lower energy, and 3 by 2 will be at higher energy. So in this way, the energy level sequence can be obtained by following the Hund's rules for highest spin multiplicity, orbital multiplicity, and J values. So with this, we have finished the discussion on the construction of microstate table for NP3 configuration. That's all.